The ones who join will wait a few more minutes to the hour, and then we start.
Okay.
Okay, it's just 10. Let's wait another minute or two, just if someone wants to assist. People are still joining. So we'll start maybe in a minute or two.
Okay.
Okay, so let's start. Welcome, everyone. We are recording this just in case someone could not join, but this is the session about the coding challenge. We have with us Georgiana Mania and Panos Adamidas from DKRZ. Welcome. Panos, maybe try to share the presentation and let's get started.
So if you can see it, then I can start.
Yeah, we can see.
Okay, then hi everyone. My name is Panos Adamidis. I'm working at the German Climate Computing Center, and together with Georgiana, my colleague, we are participating for the second year at the student cluster competition, which is within the framework of the ISC-25, which is held here in Hamburg again this year. The DKRZ is a dedicated computing center for climate science, and we are people working at the DKRZ are not climate scientists, but have more focus on IT. So I'm leading here the HPC group at the DKRZ. I have a PhD in parallel algorithms for coupled simulations from the University of Stuttgart, and prior to this, I studied computer engineering and informatics at the University of Patras in Greece. Georgiana holds a PhD in heterogeneous computing in HPC from the University of Hamburg in Germany, and she received her diploma in engineering and computer science from the University Polytechnic of Bucharest in Romania. So the hardware we have here is our Levante supercomputing system, which consists of 2,832 CPU nodes with AMD Milan CPUs, and we have in addition 60 GPU nodes, so each equipped with 4 NVIDIA A100. The total performance is 17 petaflops, and we are in the middle of a procurement, or we are starting soon the new procurement for the new machine. So the student cluster competition will run on the GPU nodes. And apart from being a computing center, some years ago, we have evolved to be also development partners of the ICON weather and climate system, which is meanwhile also open source. And this ICON model is a next generation Earth system model, but also a weather prediction model. So it's used for weather forecast and also climate simulations. The development started as a collaboration between the German Weather Service and the Max Planck Institute for Meteorology, and successively other partners joined the development because the demands of developing HPC infrastructure software grew, and this is why DKRZ has now also developed a role. The code itself that is currently used in production consists of more than 1 million source lines of code in Fortran, plus around 15,000 OpenACC directives for GPU offloading. And being a developer of a community model like ICON means that we are not only interested in having this model running efficiently on our machine, but on, if possible, all the machines in the world where users around the world can download, build, and run the model on the local machines. And what this ICON and where does the name come from? So on the left side, you see an icosahedron, which is this geometric three-dimensional body consisting of 20 triangles. And if you do a projection of this on the globe, then you will have at first 20 great triangles, which then by successively refining them and bisecting them, you can have several grids in several different resolutions. Like you see on the right-hand side, we have the Corsa grid, the red one, then a refinement over North Africa and Europe, which is the blue one, and then much finer, the black one, with even more triangles on the over Europe. And so ICON has these features which make it usable for weather forecasting, which is very the timescales are not so long, but also for at the same time can be used for doing climate simulations where the timescales are hundreds or thousands of years in the future. And the name ICON comes from this icosahedral and non-hydrostatic. The non-hydrostatic refers to the type of equations that are solved. And this model simulates many physical, chemical, biological processes in a coupled atmosphere and ocean model. Where it is used currently, the German Weather Service, DWD, and also Meteoswiss, the weather service in Switzerland, are using, meanwhile, ICON for their operational forecasting. ICON has substituted the old Cosmo model meanwhile, so it's doing real production in weather forecasting. And regarding climate science, it is one of the most used models in a variety of projects. Some of them are German-wide, other European-wide, and some of them also international. So you see here, for instance, Warm World, Next Gems, Destiny, Easy Ways, which is the Center of Excellence in Simulation of Weather and Climate in Europe. And these projects are dealing more with high-resolution climate simulations. So what this is, we will see soon. Apart from this, ICON is also used in the IPCC runs. So this is the PCC is the Intergovernmental Panel on Climate Change, which is the United Nations body which uses ICON for assessing science related to climate change. And the outcome is not only a scientific report, but it's also what it tries also to depict the consequences of this climate change on society, so that this so-called AR assessment report can be used by decision makers, which are the politicians. So this is the present, but for the future, we want to prepare the model for the exascale era, which is from the point of view of hardware, very heterogeneous, but not only from the hardware, but also from the programming paradigms that come with this heterogeneous or hybrid hardware. And so not only efficiency or speed up or increase of performance on Levante is for us important, but more important now is performance portability. And here you see a metric given by Pennycook in the paper I mentioned here, and it basically says that if your model does not run on any platform, or if it doesn't run even on one single platform, then by this definition, the portability is zero. And we have faced problems when trying to port the Fortran plus OpenSCC version to, for instance, the Lumi system in Finland, which consists of AMD CPUs and GPUs. And there we saw that it took several years, and it was not, so the build was not very straightforward. And so we focus on this problem. And we need to focus on this problem because we need exascale performance. And this comes from the fact that climate simulations are going more and more towards high resolution simulations. And what is this? What does this mean? So here you see a simplified sketch of the climate system. Or meanwhile, the word Earth system model is more appropriate and is mostly used, and not climate system, because the climate system does not contain only the atmosphere or only the ocean, but all of these processes you see here and interactions between them. So between air and the ocean, between ice and the ocean, between the radiation coming from the sun and clouds, and so on. And in order to be able to make more reliable simulations and better extrapolations or projections into the future, you need to have a model that encompasses all of these processes. One of the small scale processes that is or has been parameterized in the past is the formation of clouds. And this parameterization of the clouds introduced uncertainties in the simulations. And scientists said many years ago or so that if they could resolve the clouds, and they have the equations for doing so, but not the computational power, then the uncertainty of the climate simulations would be reduced by 50%. So this consequently means that the quality of the estimations would be then 50% higher. And so we focus on this cloud formation, but these scales are very small. So to do climate, to have a simulation that resolves the clouds, you need to go down to 150 meter or 115. We did this over Germany. But to do storm resolving simulations on a global scale, you need to go down to 1 kilometer. And this is where ICON is heading towards. And here you see the difference. On the left hand side, you see a 80 kilometer grid resolution, and you see how the clouds are represented here. And on the right hand side, you see a 2.5 kilometer grid resolution, and you see how fine the clouds are being given here. And so the corresponding simulations are much finer, and the results much better. Now, all of this has the effect that so basically you know that so global warming is coming and how. So this research has been going on now for 30 years and more, and the answers are settled somehow. But now the next step would be, okay, what is this meaning? What are the consequences? And we all know, meanwhile, and we hear it and see it, that extreme weather phenomena are coming with increased global temperature. And in order to catch this extreme weather phenomena like hurricanes and so on, we need to be able to simulate and resolve clouds. But as I said, the climate system is not only the atmosphere, it's only the ocean. And to see how good ICON is doing with high resolution, I will show you now an animation of a simulation that has been done on Levante on 900 nodes with a resolution of 1 kilometer atmosphere and also 1 kilometer ocean. What you see here is the so-called blue marble. So this is a photo taken by the astronauts of the Apollo 17 mission. And while the spacecraft was on its way to the moon, an astronaut took this picture. So here you see a real picture of our Earth. It is December 12, 1972. And now on the right, you will see a simulation of ICON. So here. So on the left is the real picture, and on the right is are the results from an ICON simulation, which has simulated how the weather or the clouds were back then. And you see the similarities are very high, and you see that this 1 kilometer scale resolution is very convincing. And now we see only the simulation, and having a tool like ICON, scientists can now make experiments, and then you see here how it, okay, this is now a scenario how it could be back in December 7th, 1972. And you see how the clouds were forming. Here you see temperature on the surface of the ocean. Here you see the eddies. Here you see both atmosphere and ocean. Now we see better the currents in the ocean. And so this is where we want to go. This is the final target. And at the end, we want to, or the scientists, the climate scientists want to use this model so as to sort of predict where the new hurricane will hit and when, or how, which areas of the earth, of the land, will be affected by the rise of the sea level, and so as to migrate people from there. If you are a mayor or a small town or village near the sea, and you know that, okay, in 2 or in 5 years my house will be underwater, so you have to move the people away from this. And this is only possible with high performance computing as much as possible, but also we need to have the proper software. And this is what we are doing, where we are working currently. And we focus again, as last year, on the part of ICON that has to do a lot with clouds, which is the microphysics or MUFIS part. And this part is calculating the different transitions of the molecules in the air from one state to another. So from cloud to ice, from there to snow or to rain or vapor and graupel, and all this arrows in between them show the different relationships and what can happen depending on the initial conditions. And this picture, although it is showing only a small part of the whole model, you see how big the complexity of the calculations are. And the task we have prepared is so we have this microphysics model as a standalone module, so which means that we don't need the full model, the ICON model, to run. So it is extracted from the ICON model. It exists as a standalone. We have input files and also reference output files, and you will work only with this microphysics code. And of course, the task is to parallelize and optimize the MUFIS code. But so this time, you will start from an existing C++ sequential implementation, and you have to first do an MPI parallelization so that we can use many nodes and have distributed memory parallelization implemented. And in a second step, you will use NVIDIA the Studpar compiler functionality for GPU offloading to target heterogeneous platforms. So at the end, you can do, of course, whatever optimization you want to achieve best execution time, but we will also this time measure also how energy efficient your implementations are. So coming to the C++ parallel standard library, which you will use for GPU offloading. So the focus is on these three header files, which you need to include in your or in your code, the execution, the algorithm, and the ranges. So the distribution of the tasks is handled then by the compiler on any parallel device, which means that if you compile for CPU, then you will have a multi-threaded version that will run in parallel on a CPU. But if we compile for a GPU, then we will have a CUDA implementation that will run then on the GPU. The data transfer is also handled automatically on the parallel execution device, so without the need of putting explicit instructions or directives or whatever. You just have to mark the pointers, and at the end of each parallel region is an implicit synchronization, but there is the need for the appropriate compilers to support this. In our case, we will use the NVIDIA compiler, NVC++, which comes from the NVHPC stack, and in version 24.7 onwards, this STUDPA offloading is being supported. In order to enable the compiler support, you have to use the flag minus STUDPA equals GPU for GPU code, or STUDPA equals multi-core for CPU parallel code. Everything sounds up to now very easy, but as usual, it is not. And as soon as you start implementing, you will face some problems. And you have to have in mind a few things. So first of all, data that is allocated on a stack will by default not be accessible from the device. So take care how you allocate your data. Your data must be captured by the Lambda, otherwise it will not be also accessible from the device. But in addition, if you are capturing data by reference, then you will have at the end a very efficient multi-threaded CPU version, but this code will not run on the GPU when you compile for GPU, because the GPUs will not be able to access this data. So you need to pass the data there by value. And if you're using as execution policy SEQ for sequential, this will always run only on the CPU. In order to get familiar with this STUDPA parallelization or offloading, here is a very simple Hello World program that you can write and execute. You see at the end the compile command. It's just NVC++ minus STUDPA equals GPU, and that's it. And here you see for each n parallel region, and this is just incrementing the contents of the vector by 1. So I would suggest for those of you who have never written a program using the STUDPA, you can start with this simple one, and then you will have some first experience, and then you can continue with microphysics code, which is in the repository. And this is how the repository looks like. I think by now, many of you, if not all, have already access. And so here you see in the we have one subdirectory called implementations. This contains now only the C++ sequential implementation, but this is the place where we want you to put your STUDPA implementation as well. And the project structure in general looks like this. So we have here some core functionality that is implemented in a way that can be used by all further implementations. So these are the general let's say things like I/O. And then in the implementations, which consists only of the sequential part right now, we have the implementation specific software. There are also some external dependencies in the external directory. And for validation, we have automated the unit tests. Our input files are in the tasks directory. Our reference results are in the reference results. And we have provided a bunch of scripts that you will use to run your task on Levante. And we did this for your convenience because I think you will struggle enough with the coding of the MPI parallelization plus the STUDPAR offloading. And so we have automated the process of building and running and also post-processing, getting the results from your implementations in several batch files, which are in these scripts directories, which we will go through within the next minutes. So at the end, you will have here in implementations your own under implementations, your own directory, STD, and here you will have the STUDPAR implementation. So now, how you do it? So we have a main, and this main program calls either the sequential or the stud implementation of the Graupel function. And the choice can be done during the build. So we have this mu_IMPL flag for implementation. And if this is set, for instance, to SEQ, then you build the sequential version. And later on, if you put your own STD implementation, then the build system can execute this command with this flag set to STD, and then the STD version of the Graupel function will be built. So for the MPI implementation, all the calls must be added only to the main. So the main is above this implementations directory. And the meaning is that we have one main, and this then calls whatever implementation we have. In our case, it will be either the sequential or the stud implementation, which you will create there. So for the parallel execution with STUDPAR, you will use 3 execution policies. So no, you will use your execution policies to the 3 main loops, which are in this graupel.cpp file. And of course, you will have to adapt the CMake list.txt files. Now we are using CMake to build everything, so it is very easy. And in the first step or the first concern you will have is to ensure correctness of the results of your implementation. After you have done this, then you can start doing several optimizations like loop reordering, collapsing or rewriting the loops however you want, minimize critical regions or optimize for cache utilization. But you have to keep also in mind that you are not writing a code only for CPUs, so cache-based programming or cache-optimized programming done for CPUs is okay, but it will give an efficient code only for CPUs. You have to take care also for GPUs. So this is the burden of portability. The setup and development of the environment is easy. So you have to load these 4 modules. So the NVIDIA HPC 24.7 compiler, the Open MPI for the MPI stuff. This is the netcdf, which is the format we use for output, and CDO, which is the tool. It's called Climate Data Operators, and this tool is used to check the results at the end. So, but you can omit all of this and just execute this levante-setup.sh script, which we have under scripts in this directory, and everything will be set up automatically for you. So for details, you can check the README. The first of your builds will be to build the existing sequential version. So this is done with this command cmake -b build, or however you name your build directory. It is important that you use this implementation, the SEQ, and as architecture, the x86-64. And we are mostly keen on double precision results. So we have also single precision, the ability, but here in this case, you will switch it off and you will give us compiler the NVC++, and that's it. Then with CMake, you will build the existing sequential version. And then when you implement your own, or the Stuttgart version, then you will have the same CMake command, but this case, you will set the mu underscore implementations to stut and the mu underscore architecture to A100. Single precision is switched off, the compiler is the same, NVC++, and then you will build your executable. And at the end, when we are going to evaluate your work, we will use this command as well. So with this settings, of course, you can and you will tell us at the end. You can use whatever compiler options you need to make it faster, but you have also at the same time to be not too aggressive and guarantee that correctness is still given. So assuming that you have written and built your executable, in this case it has the name Graupel. So in order to run it, you give the name of the executable, and then from the tasks directory, you choose. We have 3 files, rather small, which are good for development and debugging. And here it's the 11k.nc. Then you also have to specify the name of the output file, and then that's it. Then the program will run, and the output will be written in this file output.nc. And then you will use this CDO tool, this climate data operators, to compare these files. So you compare your output with the output that is given in the reference results directory of the repository. And the useful operators you see here, it's diff-v or info n minus sub. How this works, soon I will show you some examples. So for the reference results, we have for each task and for each precision, 1 file. So let's say it's 2 files per input task. So for this 11k file, we have reference results in double precision and also in single precision. So depending on what runs you are doing, you can use either one to check your results. What is our expectation? So when using no optimization flux, so O0, no FMA, and you run on the CPU, the results should be bit identical to the appropriate reference. And this is a very hard criterion because we have many implementations of the Graupel, also OpenACC, OpenMP, Cocos, SICL, because many people are working with this code, master students as well. And with all these implementations, when they run with low optimization on CPU, we always ensured bit identical results, which told us that the implementation is correct. But of course, we are keen on performance, and this is just a step, first step that shows us that the software you have written is correct. The second step is to do some optimizations as aggressive as possible, or if you run on the GPU, there the expectation to have a bit identical results doesn't hold anymore. And so there we say we give a certain threshold, and we require that your results are within this threshold. So all of this stuff can be done either one by one, executed by you, or you can use our scripts. As you see here, the last line scripts Levante minus CPU or Levante minus GPU. And submit it in the batch system, and then the script will execute everything, the building, the running, and then the comparison. So this is here a threshold for this 11K example, and we expect your results per variable. You see here the temperature, humidity. This is the cloud liquid water content, the cloud ice content, etc. Shall be within this error tolerance. So anything that exceeds this error of, let's say, 10 to the minus 7 cannot be accepted, is wrong. Everything that is below or equal to this is accepted. And this threshold comes from subtracting the or comparing the reference results, the double precision minus the single precision. And this has been proven to be a very good indicator. And this is what our users, so climate scientists or the application programmers, have suggested us as a good metric. Now, how is the validation of the stud part done on the CPU? You run your implementation on the 11K task, double precision, and then again you give your the executable, which is this Graupel. Then you select this input file from tasks the 11k.nc and give us output file the output.nc, and then you use cdo diff v output.nc. This is your output file, and compare it with the 11K double precision in the reference results file. And this results, again, on the CPU are expected to be bit identical. And if you do this with this CDO command, the check, you will see that CDO does not give you any difference in all the fields of these two files, and this is how the message would be at the end, that CDO defend processed 180,800 values from 26 variables over 2 time steps and didn't found anything. And this you will repeat also with the other tasks that are there in case you're using the others. Now, when going over to GPU, again, you run your Graupel executable with the 11K and input file, and then you do CDO info n minus zap, and then you compare your output with a reference, and then you get something like this as output. So now you don't have only this single line that we saw in the previous slide, where the differences were 0. Now you see here that there is a difference, and you see here in the temperature and the humidity it is 0, but in the other some other variables it is not 0, but it's very small. It's 10 to the minus 23 or 10 to the minus 52 or even 10 to the minus 318, which is basically 0. And so such results will be accepted. In any case, if you're unsure, then contact us via Slack. Sometimes you are so your the comparison is very marginal, and then we can decide even if you exceed in some variable the threshold that okay, it's still correct because of reasons which we need first to check. So don't hesitate to contact us regarding this. Now, once the implementation is validated, now we were talking about this serial execution up to now, or the parallel execution, but only on GPUs. You can use now high optimization flags and also enable, for instance, fuse, multiply, add, and whatever other means compilers give you to boost your code. And going now a step further to the MPI parallelization, you need here for the build process to adapt the CMake lists.txt files, not only on the root directory, but also on the subdirectories, for instance, in the implementation or wherever you add something. And in this CMake lists files, you need to put the appropriate compiler flags. And in the case of the MPI parallelization, also the paths or including the appropriate MPI library. And then after you have completed this your implementation, in order to run the parallel version, so now I'm talking about the full MPI plus C++ tutper version on GPUs, you simply use the script levante minus GPU minus energy.batch. And there you will also see that I have this environment variable multi-graupel equals to 600. So when doing energy measurements, I've seen that this kernel that you're working on is not enough or the execution of this kernel is not enough to put high load on the device so that the energy draw or the power draw is noticeable. For this, I put an artificial loop and I'm executing the main Graupel function 600 times here, so that the program is residing enough time on the device so as to do also so as to have also appropriate energy measurements. And so after running this script, you will have one file per node, which has the name you see here on the second bullet point, nvsmi.log dot the number of the job ID and the number of the node number. And don't worry, it contains a lot of numbers, but you don't need to do anything in order to make the evaluation. You just run a Python script, which is also in this script files, named process and plot nvsmi, and this will generate three graphs. The first is the speed up, as you know, over the number of nodes. The second is the power consumption. So the y-axis will have the metric watt hours, and on the x-axis again we will have the number of nodes. And then you can put the one then you can see how the speed up is. Your speed up when going from one node to two nodes run, or three nodes and four, which is the maximum. But on the second graph, you in the power consumption, you see how the energy consumption was. And a third graph tries to combine both of them. There I give the relative energy per divided by the speed up, by the speed achieved speed up on the y-axis, again over the nodes on the x-axis. So this last one, you are free to do whatever correlations you want. The first two are the essential ones. The third is something that I thought is useful, but if you have another idea, you're very welcome to put your own graph there. And this the script to run the job has, as you see, this is just an excerpt, but you see here you can build the code with this. Then you can run the executable. Here I put I export this multi-Graupel per default to 600, but if you face problems, you can set it here to 1 and while debugging, for instance, so as to work more efficiently. And then the only thing you have to do when you want to change the number of nodes for the MPI parallel execution is you set here. Now here I have that the MPI procs per node are 4, and also the GPUs per node in the srun command is 4. But you can play with this as well. I mean, if you want to have only 2 MPI processes per node, which might be a little bit slower but consume less energy, and you have then a better energy efficiency. So this is your task to find out what is then the best configuration. By using the script, everything is done automatically for you. And then when it comes to the post-processing, you have to open this process and plot NVSMI Python script, and the topmost entry looks like this. So you have here an input list, and here you have to give the path and the files, this nvsmi.log files, which I mentioned earlier. And here I have an example of some of my own icon runs, not microphysics, but the full model. And here you see the first entry, I named it 01, is a test on one node with one GPU. And this is how the file looks like. And then when I run this, the previous script that I show you on, then I run it on 3 nodes. And here you see I have 3 nodes with 4 GPUs per node. And then I'm getting again 1 log file per node. And then I did a run on 4 nodes, again 4 nodes with 4 GPUs, and then I have 4 files, 1 per node. And then you have to copy and paste. This is how I did it, because I'm not a skilled Python programmer, but if you find a better way, please go on. And this is the only place in this Python script where you need to put to make your changes, to tell the script where the files are. And then you have to, on Levante at least, module load Python 3, and then you just execute Python process and plot nvsmi.py. And then the results, the graphs, the plots are done automatically by this script. The script scans all these files and gets the appropriate data. So how is the evaluation done? Each team needs to submit in the associate working directory on Levante the path to the implementation, the scripts to build CPU and GPU executables for performance, the Slurm logs to confirm the results they will submit, a summary list of optimizations performed, plots to confirm performance results, also profile analysis, output and interpretation. And the best thing would be to have this in a PDF report, where you also report about your experience for using StudPar. So this way, this programming paradigm of C++ StudPar for offloading to GPUs is something that, apart from Georgiana, nobody else has tested here at DKRZ. So now you will be, you are the second guys working with this, and we are very keen on your results and what you report to us. And the grading, we will run ourselves your code, of course, and this will be evaluated on Levante, and we will compare it, of course, with a sequential version on a large netcdf file. This time we will give you the netcdf file, not this last year, where we didn't give it out, but kept it just for evaluation for us, because you need a large file to run the MPI parallel version. So this file is large enough so that it does not fit into this repository. So in a few days, we will announce a folder on Levante where all of you can access this file. But I think you will have enough coding work to do in the next weeks with the MPI parallel version and the Studpro version, so that you are not you do not depend immediately on this large file. But so until the end of this week, maybe early next week, the latest, we will announce where this file is and how you can get it. And for the grading, so 50% will be given to the fact of compiling compiled code using the commands you will provide us and your flags, and a code that runs on both on CPU and GPU and gives us correct results. And then the other 50% of the points will affect the achieved speed up relative to the sequential version, but not only the speed up, but also the energy efficiency, because we want to see what is the lowest power consumption. So this changes a little bit the metric, and not the fastest will win, but the one with the most or the most energy efficient. And again, for correctness, bit identical results are required for CPU, and staying within the thresholds as shown on the slide 28 for the GPU. And that's it from my side. Now I'm open to questions.
Thank you, Panos. I hope it was not too much overwhelming for the teams.
Yes.
It was a lot of information.
Everything is written also on the wiki, and I think we will put also the slides there, and they can then ask us.
Yeah. Anyone has any questions? Of course, you can also approach us later on. Anyone has any issues with the connectivity to Levante? Panos, did they all get the access?
Yes.
Did we have any?
All teams that have applied have access to Levante and also to the GitLab. So I have seen that there are many teams in both the GitLab and.
If for some reason some team have some difficulties, let us know.
Yes. And contact me immediately, and we will settle it. Yeah.
And if you have any questions, anything, we're happy to help. So contact us via the team channel on the Slack, and we'll try to address it. Anyone, any questions now? No questions? Everything is, everyone understood, Panos. They know everything.
Yeah. Yeah, this was the goal, because I know that that the task is a bit difficult. We put in the slides all the steps that are needed, so that it is sort of a manual, so that they can go to the slides and see which commands they have to execute and when and why, and so.
Alexander, do you want to say something?
Yes, right. Can you hear me?
Yeah.
Okay, perfect. So I already looked at the code, and there was this precip function. I wonder if you came up with this function by yourself, or is there any paper which we could read to maybe also improve some algorithmic things?
This code was written by the meteorologists at the Max Planck Institute for Meteorology. So I'm sure that there are also papers about this, but we don't have them. So
All right.
Georgiana wants.
Yes, I wanted to mention, I think the task is more like a computer scientist point of view on the algorithm. So if you maybe have in mind some optimizations regarding, I don't know, performance or the memory, things like this would be actually needed more than actually rewriting the algorithm. I think the algorithm is pretty old, maybe 20 years or so, and it has been rewritten by meteorologists several times to make sense for them. So I wouldn't necessarily try to optimize necessarily that. Maybe the order of the loops or things like that, but not the algorithm itself, I think.
Yeah, okay, all right. That's already what I thought about, because it was already difficult to understand what was behind this variable name. So, all right, yeah, thank you.
I think for a meteorologist, the variable names make sense. For us as computer scientists, might not make so much sense, but we try to keep that as similar as the original code was, so they can follow it later on.
Anyone with more questions? Welcome. Okay, if no other questions, I want to thank Panos and Georgiana, and again, start looking into that. We'll be happy to help, along the way, and let's see what we can come up with. And good luck, everyone.
Yeah, good luck.
Okay. Okay, guys, let's close the sessions. We'll see you tomorrow with the applications. Okay, check the website for the times, and we'll see you all tomorrow. Good luck. Bye bye.
Bye.